Understanding Parametric Equations. Hello everyone. Today, we are going to begin our lesson on understanding parametric equations. To start, let's reflect on what you have already learned. In your previous study of calculus, you have primarily encountered functions where one variable is expressed directly in terms of another. For example, consider an explicit function such as y equals 2x plus 3. In this specific case, the variable y depends directly on the value of x. If you change x, y changes immediately. However, as we move into more advanced mathematical and physical scenarios, you will find that x and y are not always directly linked to one another. Instead, they both depend on a third, independent variable. This third variable is known as the parameter. In the upcoming slides, we will define exactly how this parameter works and see how it acts as a bridge to connect our x and y coordinates. What are parametric equations? Now that we have introduced the general concept of a parameter, let us move on to the formal definition of parametric equations. A pair of equations is said to be in parametric form if both the x and y coordinates are expressed as functions of a third variable. In your studies, you will find that this third variable is most commonly denoted by the letter t, often representing time, or the Greek letter theta, which typically represents an angle. To express this mathematically, if we have two functions, which we can call f and g, that both depend on the parameter t, then the parametric equations are represented as x equals f of t and y equals g of t. In this setup, it is important to understand the relationship. X is a function of t, and y is also a function of t essentially. The variable t acts as the bridge or the parameter that connects x and y. Unlike the explicit functions we discussed in the previous slide, where y depended directly on x, here they are linked indirectly through t. This distinction is crucial. And in the next slide, we will compare this parametric form with the Cartesian form to see exactly how they differ. Parametric versus Cartesian forms. Now that we have established the basic definition of parametric equations, let us compare them with the Cartesian form to better understand the distinction between the two. First, let us look at the Cartesian form. This is the standard representation you are likely already familiar with, where the relationship between two variables is expressed as a single equation involving x and y. For example, consider the equation of a circle. X squared plus y squared equals r squared. In this form, the relationship between x and y is direct and contained within one single expression. In contrast, we have the parametric form. Instead of a single equation, this method breaks the relationship into two separate equations, each of which depends on the parameter we discussed in the previous slide. To illustrate this using the same circle, we can use the angle theta as our parameter. The relationship is then expressed as two equations, x equals r cosine theta and y equals r sine theta. By separating the coordinates this way, we gain more flexibility in how we describe the curve. In the next slide, we will see how this flexibility is incredibly useful when analyzing real-world scenarios, such as projectile motion in physics. Real-world application, projectile motion. Now that we have compared the Cartesian and parametric forms, let us look at how this actually applies to the real world. A classic example of parametric equations can be found in physics, specifically when studying projectile motion. To visualize this, imagine a ball being thrown into the air at a specific angle. As the ball moves, its position at any given moment is described by two different values: its horizontal distance, which we represent as x, and its vertical height, which we represent as y. It is important to notice that both the horizontal distance x and the vertical height y are changing simultaneously as time, represented by the variable t, progresses. If we look at the mathematical formulas for this motion, the horizontal position is defined as x equals v0 times the cosine of alpha, multiplied by t. Meanwhile, The vertical position is defined as y equals v0 times the sine of alpha times t, minus 1/2 gt squared. In this scenario, time, or t, serves as the parameter. Notice that we do not start with a simple equation where y is a direct function of x instead. We determine where the ball is located both horizontally and vertically based on how many seconds have passed since it was thrown. Having seen this physical application, we will now move on to a purely mathematical example to see how these equations define a curve on a graph. Step-by-step example of a parametric relation. Now that we have seen how parametric equations apply to real-world physics in the previous slide, let us look at a simple mathematical example to see exactly how these equations define a curve on a graph. Please direct your attention to the given equations, x equals 2t and y equals t squared. In step 1, we must identify the parameter. In this specific case, the variable t is the parameter. As we established in our earlier discussion, this means that both x and y are defined in terms of t, making t the bridge between the two coordinates. In step 2, we will examine the dependency by choosing a specific value for our parameter. If we let t equal 1, then x becomes 2 times 1, which equals 2, and y becomes 1 squared, which equals 1. This results in the coordinate point, 2, 1. In step 3, we repeat this process for another value to see how the point shifts. If we choose t to be 2, then x equals 2 times 2, which is 4, and y equals 2 squared, which is also 4. This gives us the point, 4, 4. By continuously varying the value of t, we generate a set of points, x, y, that form a continuous curve in the Cartesian plane. This demonstrates how the parameter controls the movement and shape of the graph, a concept we will summarize in our key takeaways in the next slide. Key takeaways. Now that we have walked through the theoretical definitions and a practical example, let us consolidate our understanding with these key takeaways. First, let's recap the concept of the parameter. As we have seen in our previous examples, the parameter is a third independent variable, typically denoted by the letter t or the Greek letter theta, which serves as the primary driver to define the values of both x and y. Secondly, we have the parametric form. This refers to a system of equations where x is expressed as a function of t, and y is also expressed as a function of t rather than one single equation. We use this pair of equations to describe a single curve. This leads us to the idea of independence. It is crucial to realize that in parametric form, x and y are not directly dependent on each other. Instead, they are both independently dependent on the parameter t. Think of it as the bridge we mentioned earlier. X and y are connected only because they both rely on the same third variable. Finally, let's consider the utility of this approach. Why do we use this instead of standard equations? As we observed with the circle and the projectile motion example, parametric equations are exceptionally useful for describing physical motion and complex curves, such as ellipses. These are often very difficult, or even impossible, to express as a single function where y equals f of x. Now that we have a firm grasp of these fundamentals, let us move to the final slide to discuss some common mistakes you should avoid when working with these equations. Common mistakes to avoid. Now that we have explored the concept of parametric equations and seen how they apply to real-world scenarios like projectile motion, let us conclude by discussing some common pitfalls to avoid. First, be careful not to confuse the parameter with a constant. A frequent mistake students make is treating the parameter, such as t, as a fixed number. It is important to remember that t is a variable that changes. As we saw in our previous examples, as t varies, it simultaneously drives the changes in both x and y. Second, avoid the assumption that y is a direct function of x. In the beginning of this lesson, we discussed explicit functions where y depends directly on x. However, in parametric form, this is not necessarily the case. Instead, you must recognize that x and y are essentially independent of one another, and both are instead dependent on the third variable, the parameter t. Finally, let us address incorrect substitution. As we move forward, you will learn how to convert parametric equations back into the Cartesian form, like the circle equation we looked at earlier. The most common error here is failing to remove the parameter entirely. When performing this conversion, ensure that the parameter t is completely eliminated from both equations, leaving you with a final relationship expressed only in terms of x and y.